Welcome to the Yaka Digital Network. Look closely at this locally fabricated metal stove. Before it took this cylindrical shape, it began as a flat sheet of metal. Converting that flat sheet into a functional 3D object requires surface development. In engineering, development is the exact method of stretching out or unfolding the entire surface of a three-dimensional solid onto a flat two-dimensional plane so it can be accurately cut and formed. This animation shows a cylindrical water tank as it unrolls into a flat rectangle. This specific process uses our first foundational technique, parallel line development. We apply this method to objects that maintain a constant cross-section throughout their entire length, such as cylinders and uniform prisms. Because the shape doesn't taper, the lateral surface is developed by projecting lines strictly parallel to the object's central axis. To successfully draft this development for standard UNEB examinations, you must follow a strict 5-step sequence. First, draw the orthographic views to identify true dimensions. Second, determine true lengths if necessary. Third, establish your horizontal stretch outline, which equals the total perimeter. Fourth, project vertical lines to transfer your points. And fifth, add your required seams and allowances. Parallel line development ensures precise material efficiency. By projecting lines parallel to a constant axis, the method provides a mathematically accurate one-to-one translation from your 3D design to the flat 2D sheet. Here, we have a 3D model of a truncated pyramid next to its standard orthographic front and top views. Objects like this pyramid, or a tapering cone, all slant toward a single common apex. Because the cross-section shrinks as it rises, parallel projection is no longer sufficient. We must instead use radial line development. Consider the slant edge on the 2D front view. Because that edge physically angles away from you in three-dimensional space, the line drawn on the flat page is foreshortened. It represents a distance that is shorter than the actual physical material required to build the object. We find the correct dimension by determining the true length. By anchoring a compass at the apex in the top view and swinging the angled slant line until it sits parallel to the reference line, we project that edge flat. Projecting this new point down to the front view gives us the mathematically accurate length of the actual material needed. Now we use that specific true length as our radius. By anchoring at the apex, we swing an arc. This arc forms the primary stretch-out line for radial development. We then divide the base and the plan view into equal parts and transfer those exact lengths directly onto this sweeping arc. Without verifying the true length, the resulting stretch-out arc will be too tight. The material will be cut short, and the final metal piece will warp and distort when you attempt to fold it into its final 3D shape. Look at this flat pattern layout. In a busy workshop, a fabricator needs to know exactly what to do with a sheet of steel. Based on standard engineering conventions, how would a technician distinguish between the lines meant for the cutting shears and the lines meant for the folding machine? You have 5 seconds. The convention is strictly defined by line weight and type. Continuous thick lines dictate the outer boundary of the object. This is where the material will be cut. Thin dashed lines indicate the internal divisions. This is where the material should be folded. Notice this extra material extending from the edge. When calculating your final layout, you cannot simply draw the exact dimensions of the faces. You must add a seam allowance. This extra flap provides the physical overlap required to rivet, solder, or fold the two ends together so the shape stays closed. A mathematically perfect geometric layout will fail on the workshop floor without these practical additions. Proper line conventions communicate the instructions, and precisely calculated allowances provide the material needed to secure the final joint. This image shows an industrial coffee roaster in operation. Consider a practical design scenario. A roasting company in Bale needs a custom stainless steel hopper. The design requires a square 200mm opening at the top that transitions into an 80mm circular outlet at the bottom to feed the grinder. We are seeing a 3D model of that exact square to round hopper. Because this transition piece lacks a uniform cross-section and does not taper to a single apex, both parallel and radial development methods will fail. Instead, we use triangulation. This method breaks the irregular, warped surface down into a series of smaller, perfectly flat triangles. Watch as a single triangle peels off the wireframe. Because the corner ribs slant irregularly, we must construct true length diagrams for every side of every triangle. Once the true lengths are confirmed, we draw the triangles side by side in succession on our flat sheet until the entire warped surface is laid out. This comparison table maps out exactly when to use each approach. Parallel line development is for constant profiles like prisms and cylinders. Radial line development is for single apex tapers like cones and pyramids. And triangulation handles the irregular transitions. By accurately matching the 3D shape to the correct development method, projecting your true lengths, and securing your practical workshop allowances, you ensure that your flat designs will ascend perfectly in the real world. Thank you for learning with the Yaka Digital Network. Visit us at yaka.cc for more resources.